Morning.
Good morning.
ಹಬ್ಬ ನೀನು ಒಬ್ಬ ರಿಪ್ಲೈ ಮಾಡ್ತಿಲ್ಲ, ಸಾಕ್ಬಿಡ, ಖುಷಿ ಆಗ್ಬಿಟ್ಟೆ ನಾನು.
Sir.
ಯಾಕೆಂದ್ರೆ ನಾವ್ ಯಾರು ಗುಡ್ ಮಾರ್ನಿಂಗ್ ಹೇಳಿದ್ರೆ ಅಟ್ಲೀಸ್ಟ್ ಗುಡ್ ಮಾರ್ನಿಂಗ್ ಹೇಳ್ಬೇಕು ಅನ್ನೋದು ಗೊತ್ತಿಲ್ಲ. ಆದರೆ ನಮ್ಮ ಹುಡುಗರಲ್ಲಿ ಒಂದು ಒಳ್ಳೆ ಗುಣ ಏನು ಅಂದರೆ, ನಾನು ಟುಡೇ ವಿ ವಿಲ್ ವೈಂಡ್ ಅಪ್ ದ ಕ್ಲಾಸ್ ಅಂತ ಹೇಳಿದ್ರೆ ಅಟ್ ದಟ್ ಟೈಮ್ ಎವ್ರಿ ಒನ್ ವಿಲ್ ಟೆಲ್ ಥ್ಯಾಂಕ್ ಯು ಸರ್, ಓಕೆ ಸರ್, ಥ್ಯಾಂಕ್ ಯು ಸರ್, ಥ್ಯಾಂಕ್ ಯು ಸರ್, ಥ್ಯಾಂಕ್ ಸರ್ ಅಂತ ಹೇಳ್ತಾರೆ. ಸ್ಟಾರ್ಟ್ ಮಾಡ್ಬೇಕಾದ್ರೆ ಮಾತ್ರ ಒಬ್ರು ಹೇಳಲ್ಲ ಅಟ್ಲೀಸ್ಟ್. ಅದಕ್ಕೆ ಆಫ್ಲೈನೇ ಬೆಸ್ಟು. ಅಟ್ಲೀಸ್ಟ್ ಮರ್ಯಾದೆ, ಅಟ್ಲೀಸ್ಟ್ ಗುಡ್ ಮಾರ್ನಿಂಗ್ ಹೇಳಿದ್ರೆ ಹೇಳ್ತಾರೆ. ಹ್ಞೂ ಸರಿ ಬಿಟ್ರು, ಏನೋ ಒಂದು ನಿಮಗೂ
ರೀಚ್ ಕ್ಯಾರೆಕ್ಟಿಂಗ್ ಅಲ್ಲ ಸರ್, ಅದಕ್ಕೆ ಹಿಂಗೆ.
ಏನು ಹೇಳ,
ವಾರದ ಮೊದಲನೇ ದಿನ ಅಲ್ಲ ಸರ್, ಅದಕ್ಕೆ
ವಾರದ ಮೊದಲ ದಿವಸ.
ಮಂಡಿ ಪ್ಲೀಸ್.
ನಮಗೂ ವಾರದ ಮೊದಲನೇ ದಿವಸನೇ ತಾನೆ, ನಿಮ್ಮ ಥರನೇ. ಜೋಶಲ್ಲಿ ಇರಬೇಕು. ವಾರದ ಮೊದಲನೇ ದಿವಸ ಫುಲ್ ಎಂಜಾಯ್ ಮಾಡಿರ್ತಾರೆ ಲಾಸ್ಟ್ ವೀಕು. ಇವತ್ತು ಬಾ ಕ್ಲಾಸಿಗೆ ಬರೋಣ ಅಂತ ಹೇಳ್ಬೋದು. ಹೋಗ್ಲಿ ಬಿಟ್ರೆ.
ಏನ್ ಎಂಜಾಯ್ ಸರ್, ಏನಿಲ್ಲ.
Okay, so we'll just start with today's class. Okay, thank you. In the last class, we were discussing about some of the converters. So, in which I was just considering about in the fifth model I just started, and in that I just started with the binary weighted resistor DAC. So, in which I used to give the digital input, so correspondingly, so output will be in the analog form. So, that is for 4-bit binary weighted resistor DAC, we have just seen the circuit, so architecture, as well as the working of that 4-bit digital to binary, sorry, digital to analog converter we have seen. So in that we have seen the output. So for every bit so we have seen, so the register, if we come into the architecture wise, so we can see the register has been scaled down in the terms of binary itself. So first register, which is going to be for the first bit, so B0, B1, B2, B3. So we have just taken 4-bit binary weighted register tag. So in which for the B0 bit, so we have connected the resistance R. So for the B1 bit, we have scaled down the resistor to R to the power of 2 power 1, and for the B2 bit, we have scaled the resistor value by R divided by 2 to the power of 2 square, and for the B3, so R divided by 2 power cube. So like that we have scaled down the resistance value, and we have connected the reference voltage, which is to be connected for this 4-bit digital to analog converter. So for which we have given the binary logic high as P reference is equal to 5 volts, and if I want to connect 0 to the corresponding bit position, means we are going to use the ground. So this logic high corresponds to plus 5 volts, and logic 0 corresponds to ground. So in this way we have been connected for this corresponding 4-bit inputs. So since it is going to have 4 bits as an input across the input side, so we have 2 power 4 16 combinations as a output combination will be getting, starting from 4 zeros to 4 ones. So 0000 to 0001. And if we look at this for its corresponding bit position, so we can see the inverting amplifier has been connected. So by the auto binary weighted register DAC output will be connected to the inverting amplifier, so that you are going to get the output in the analog form. So another important thing we need to identify is that since it inverting amplifier is being connected, so the output will be having inverted, that is a negative output will be getting. So because the output will be inverting, because it is the input has been connected with the inverting input. So because of that, we can see the analog waveform. So we'll be getting the staircase waveform. So this will be also called as a staircase waveform. So but it is in the negative way. So you can see inverse negative staircase waveform. So if we have connected to the non-inverting terminal, means so you'll be getting the positive staircase waveform like this. Whereas since it is connected to the inverting amplifier configuration, we will be getting the negative staircase waveform. So for this, instead of connecting bit by bit positions, we can connect on 7493 counter, which is going to have a 4-bit binary counter. So based upon that binary counter, so it is going to count from 0 to 1. So 0 to all zeros to all ones. So that in that way, So it is going to connect each bit positions so that you will be getting all the possible 16 possible output you will be getting. So you will be getting the first bit when all the bits positions has been 0, so it is required that so there will be no current flowing from this to the inverting amplifier, and hence so in the through the feedback resistance also there will be no current, and hence the output voltage will be held at 0 potential. So 0 output voltage will be getting. So this is about the 0 when all the bit positions are being connected to ground. We know that from all the bits position can be connected from all zeros to all ones. So 1 indicates +5, 0 indicates ground. So when all the bits are 0, 0, 0, so it will be connected to ground. So output will be 0. So the next bit position is whenever the bit position B0 is being connected to the plus 5 volts. So you can see this is a configuration. Then rest all the bit positions so has been connected to 0. So B1 bit has been connected to ground. So B2, B3 both have been connected to ground. So when this bit is corresponding bit has been connected, so you can see corresponding 5 volts will be applied. So we can easily find out the current. So current is equal to 0.5 milliamps. So since we are going to have resistance and the voltage has been there, so it will be the current will be flowing. So this current will be flowing through the feedback resistance itself because the it is connected in the non-inverting. So the non-inverting terminal is held at ground potential. So obviously, so node V2 is also will be at virtually ground. So all the current will be flowing through the feedback resistance RF, and hence the output voltage will be getting as a minus 0.5. So here we have connected RF as 1 kilo ohm, and this will be R as 10 kilo ohm. So you will be getting the output voltage will be equal to minus 0.5. So this is the minus 0.5 voltage for the bit position when the B naught is 1. So now similarly, if I want to have so second bit so position B1, so we have since scaled down the resistors by R by 2. So the current flowing whenever it is being connected to this plus 5 volts, so obviously the current which is going to flow in this arm will be greater than this one. So because it is scaled by 2, hence the resistance is less, whereas the correspondingly voltage is being constant, but the resistance is less. So the current flowing here it will be two times two times. So okay, it is double that of the current that is flowing over here. So that this point, so this will be equal to 1 milliamps of the current will be flowing. And since the resistance across this is very small, so it will be going to flow across the RF itself, and none of the current will be flowing across the inverting terminal, and hence the current output voltage will be getting as a minus 1 volt. So like that you can see whenever the bit position B1 is connected to 1, so if all the other bits have been 0, 0 means, so obviously this 5 volts divided by 2.5 V by R is equal to I, so the current will be equal to I divided by 2.5, 1.5 milliamps will be current will be flowing, and hence the output will be 1.5. Okay, so 1.5 volt will be getting. So here 5 divided by 1.25, so obviously it will be equal to 4 volts will be getting as the output. So in this way, so in this corresponding all the bits position have been connected to 5 volts means we will be getting the full scale reference voltage that will be equal to minus 7.5 volts. So this is about the binary weighted. So in this bit we have seen that even though the circuit is simpler and the circuit is simpler, but the values of the resistance which you are going to connect, so for as the number of inputs is going to increase, so it is going to be very difficult to find out the exact value. So if we are not getting exact value, then that means we will be not getting the actual output, and hence so this type of binary weighted rack is suitable only for the less number of inputs, that is that too it will be less than number of 4, so this will be best suited. So this is about the binary weighted DAC architecture. So now coming to the also coming to the how you are going to get the output voltage. Since it is inverting amplifier, you will be having minus RF divided by R. Whereas since the value of the resistance here we are going to have difference in the values for each of the arms, so you are going to have for that corresponding bit position, whenever it is bit position is 1 or 0, that is going to be given by this sum. So B0 by R, B1 by R by 2, so B2 by R by 4 plus B3 by R by 8. So this is the weighted sum. So this is the weighted sum of all the bits, so that when corresponding bit position is 1, so you can substitute the value of 1 and you can find out the corresponding output voltage. So this is the this is how you are going to get the output voltage. So next is in this digital to analog converters, in order to overcome the resistance selection problems which was there in the binary weighted tag. So we are going for R and 2R architecture. So in which so we are going to deal with only two resistors. One is R, that is going to have a specific value, and correspondingly we are going to select the 2R resistors. So by using R and 2R resistors, so you are going to convert the architecture is going to convert from digital to analog conversion. So in this we are going to deal with only two resistors, R and 2R resistors, and through this only, so you are going to convert the resistors. Through this only, you are going to convert the digital input signal to corresponding analog output. So we will see so how the architecture is going to work, and we need to verify whether this architecture is best suited. So for that we need to find out what is the voltage across each terminals, and we need to find out what Thevenin equivalent voltage, Thevenin equivalent resistance also we need to find out. So the binary inputs are switched given by the switches through the B0 to B3. So we know as it is in the previous case. So in this, since it is a binary, that is a digital to analog converter, the inputs are being given through the switch, so B0 to through B3, so B0 being LSB and B3 being MSB. So most significant bit is B3 and the least significant bit is switch is B0. So B0 through B3, so it is a 4-bit R2 to R ladder type. So and the output is proportional to the binary input. So because of hence we will see how it is going to have. So whenever this bit position is being connected to plus 5 volts, it is nothing but a logic high, and whenever this bit positions are connected to the ground, so that is nothing but a logic low state. So binary digital input 1 and 0, we are going to have plus 5 volts as well as 0 volts respectively. So that is a reference voltage. So assume that MSB bit position is B3 is connected to plus 5 volts. So in this architecture we will see, so what is the R2 to R ladder architecture. This is a R2 to R, so have output, and through which you can see 2R R. So this is nothing but a R 2R combination. So through which you are going to have R and 2R configuration. So R 2R, R 2R, and 2R will be the final, and another 2R will be connected in the architecture so as to maintain the uniform proportional resistance. So when you calculate each of the resistance, so you will be getting them if you find out the equivalent resistance when all the bit position is connected to 0 means you will be getting the resistance value will be equal to R. So you can see. So suppose if all the bit positions are this, then if you find out the equivalent resistance or Thevenin equivalent resistance, if you find, so 2R parallel with 2R. So since all the bit positions, suppose in the first case if you consider, so B0, B1, B2, B3 being the switch which is being connected to either plus 5 volts or to being connected to ground. So if all the bit positions are being connected to 0, so that means here there will be no equivalent, that means there is no voltage drop, so that there will be no current that will be flowing through the feedback path, and hence the output voltage will get settled at so V0 will be equal to 0 volts respectively. So if you find out the equivalent resistance over here, so 2R parallel with 2R, so it will be equal to what? So 2R into 2R divided by 2R plus 2R. So 4R square divided by 4R, so it will be equal to R. So if you find the equivalent, so we can, so this will be the R. So this equivalent resistance R will be in series with this, so it will become 2R again. So 2R parallel to R, again the equivalent resistance will be R. So that R will be in series with this, so 2R parallel to R, so again it will be equivalent resistance is R. So R plus R is 2R, so 2R parallel with 2R, so you will be having the equivalent resistance of all the things whenever it is connected to 0, so it will be equal to R itself. Okay, so this will be equal to R. So RF by R, so since it is an inverting amplifier, so equivalent resistance if it will be equal to R, so that means we will be having RF by R as the gain, minus RF by R will be the gain, and corresponding output voltage we will be getting. Suppose we will see, so if the bit position 3, switch B3 is connected to plus 5 volts respectively. So that means if the B3 position, if it is connected to plus 5 volts, and rest all the bit positions of B1, B0, B1, B2, if it is connected to ground, so that means this will be connected to plus 5 volts. So correspondingly we need to find out what is the equivalent resistance up to here. and then we need to find out the value of this, and we need to find out what is the amount of current that is flowing. So when B3 bit position is connected to logic high. So when B3 bit position is connected to logic high, so what is the node voltage across here? So that is nothing but a V2 node voltage. So here also node voltage will be same, here also node voltage will be same. So I need to find out what is the voltage at this corresponding node. So in order to find out this corresponding voltage at this corresponding node, so I need to find out the equivalent resistance up to here we need to find out. So that is the Thevenin equivalent voltage we need to, Thevenin equivalent resistance we need to find out. So as I told, so this will be equal to, so you have to make sure that whenever this bit position is 1, so you have to see what is the resistance over here. So 2R parallel to R, so that will be equal to R plus R 2R. So 2R parallel to R, that will be equal to R. So R plus R 2R. So 2R parallel to R, it will be equal to R plus R, it will be equal to 2R. So up to here if I find, so up to here the equivalent resistance will be equal to 2R respectively. Okay, so up to here this position, so we will be having, so what is the equivalent resistance? So it is equivalent resistance is 2R. And here since you're going to have a direct connection, so we'll be having the 5 volts drop. So whenever this 5 volts is being connected through the resistance having 2R and 2R respectively, so obviously, so 5 into 2R divided by 2R plus 2R you will be getting. So this gives the voltage across this point will be finding. So what is that equivalent voltage? So 5 into 2R divided by 4R. So 2R divided by 4R means it will be equal to 1 by 2. So 5 divided by 2, so that will be equal to 2.5 volts respectively we will be getting at this position. So if we find, so this node position, so we will be having what? So 2.5 volts respectively. So 2.5 volts and the correspondingly the current which will be flowing, so we need to find out. So we are going to have this equivalent, so you can see the Thevenin equivalent resistance from across from this part, so you can see up to here. So the Thevenin equivalent resistance will be equal to 2R, and this will be the 2R resistance for which the bit position is given as the equivalent circuit has been written. So plus 5 volts and plus 5 volts, the value of the current which is flowing over here. So it will be having the 2.5 volts. So 2.5 divided by 2R. So that will be the amount of current that will be flowing. And so since it is being connected to the inverting amplifier, so inverting amplifier input equator. So what is the gain we'll be getting? Output voltage we need to find out. So V naught will be equal to minus R, so minus R by so sorry, I minus I into R if I'm going to find, then obviously you'll be getting the output voltage V naught. So V naught will be equal to minus I into RF, so that will gives the output voltage. So this is about the circuit configuration for what? So this is whenever the bit position B3 is connected to 1. So obviously this part is remains same, so inverting amplifier configuration, so with the non-inverting terminal being connected to ground and the inverting terminal being connected to being connected to the feedback. So this feedback resistance has been connected to inverting terminal, so in this corresponding V2 will be also be virtually ground, will be held at virtually ground. So almost all the current will be flowing across this, will be flowing across the feedback resistance. This feedback resistance we are going to use a 20 kilo ohms. So now if I want to find out the corresponding bit position, so B3, when B3 is equal to 1, so in this case we will be getting this as the output position. So when B3 is equal to 5 volts, what is the corresponding output voltage? So you will be getting, so 5 volts is there. So in that correspondingly, what is this around 2.5 volts is there, right? So when B3 bit is 1, so you will be getting 2.5 volts. So what is the current? So 2.5 divided by what is the 20 kilo ohms? So that will be nothing but 1.25. So 1.25 milliamps will be current will be flowing. So 1.25 into 2, that will be equal to 2.5 volts. So that will be 1.25 2.25 into 2, so that will be equal to minus 5 volts will be getting. So easily whenever the bit position is equal to 5, so we will be getting the minus 5 volts. So we will see one by one bit position. So the same thing, so which have been obtained for the previous, so we will be getting the same. So B3 divided by 2R. So this is nothing but the, so whenever this bit position is connected to 5 volts, so this node voltage, so this at this node point, so B3 divided by 2R you will be getting. So whereas so for that bit position, the B2, whenever the B2 bit position is being connected to 1, rest all the inputs are being connected to 0, so you'll be getting so B2 divided by 4R and plus B1 divided by 8R plus B0 divided by 16R. So we will see how we will be getting this expression. Okay, so bit by bit position we can see this is the expression which I have written. So this is nothing but a circuit diagram of R2 to R ladder tag. So now we need to find out what is the node voltage. So when suppose if I am going to select only whenever B0 bit position is connected to 1. So that means whenever it is connected to plus 5 volts, so rest all B1, B2, B3 bit positions have been connected to 0. So what is the node voltage across here we need to find out. So similarly when this bit corresponding bit is going to connect, so we need to find out what is this node voltage and correspondingly B2 as well as B3 respectively. When all the bit position has been connected, so you will be get sum up with this one. So this is nothing but B3 by 2R, so B2 by 4R, B1 by 8R, B0 by 16R you will be getting. So this we can see here. So first we need to find out what is the voltage, corresponding node voltage across here we need to find out, and then correspondingly we can sum up all this voltage to get the final output voltage respectively. Suppose B0, hello, Amsa. So now we can see, so in this auto to R, so when the B0 bit position is connected to logic high, so the reference voltage is given as 5 volts. So when this B0 is connected to logic high means it will be connected to plus 5 volts, and the rest all B1, B2, B3, B1 bit uh, so B1, B2, B3 will be connected to ground. So if all these bit positions have been connected to ground, so we can see B0 is equal to logic high and the B1, B2, B3 will be connected to ground. So what is this corresponding node voltage we need to find. So 5 volts is given, so 5 into, so corresponding equivalent. So we need to find out what is this equivalent voltage across here. Okay, so we need to find out the equivalent. So I'm going to write the same circuit in this one. So 5 volts will be taken as a reference, and this is the 2R is the resistance which has been connected directly, and this is the parallel combination 2R will be having. So 5 into 2R. So at this point of node voltage, what is this voltage we need to find? Me 5 into 2R divided by 2R plus 2R. So that will be equal to, that we are going to write. So V reference into 2R divided by 2R plus 2R. So that is the Thevenin voltage. So at that Thevenin voltage, what is the V naught we need to find out. So at V naught we are going to find out as so 5 into 20k divided by 40k. So 4R means R is equal to 10k. So here we are going to see. So R is equal to 10k means 2R means 20k. So here 4R means 20k divided by 40k. So it will be having 5 by 2. That is the 2.5 volt as that at this corresponding node voltage. So whenever this position is 1. So you will be getting at a node voltage V0 position will be equal to 2.5 volts. So similarly, so in order to find out the Thevenin equivalent resistance, so we need to disconnect this and we need to find out it should be connected to ground. So that we will be getting, so 2R with will be parallel with the 2R. So 2R parallel with 2R means what is this equivalent resistance? So equivalent resistance will be equal to R respectively. So you will be having equivalent resistance as R. So and then correspondingly will be the equivalent resistance you will be getting as a R. So now in order to get this bit position B1 whenever it is connected to 1, so we need to find out what is the voltage at this point respectively. So in order to find out this voltage, so V1, so what will be the voltage? So we need to find out what is the voltage at V1. So if I am going to have 5 volts over here being connected, so when only when this voltage is being connected, so what is this 5 volts, and we know that what is the equivalent resistance over here. So R will be there, so R plus R 2R will be there, so same thing. So here we are going to have, so here it will be having 2.5 voltage respectively. So this here it will be having 2.5 respectively voltage, and you will be having only with respect to this V reference. So at this node voltage V naught, so it will be acting as a V reference. So V naught will be acting as a V reference now, and the remaining thing. So we can easily find out what is the corresponding voltage at this point. So 2.5 volts, and so what is the 2.5 volts? So reference voltage will be there. So 2.5 into, so at this position what is the voltage to find out means, so 2.5 into 2R divided by 4R respectively. So V reference into 2R, so V reference is this, so into 2R, so into 2R divided by 2R plus 2R 4R, so it will be equal to 1.25 volts. So when 1.25 volts alone. So similarly, so at node 2, so here I have calculated. So similarly, so if I want to find out the equivalent resistance of this configuration, so this reference voltage need to be connected to 0. So 2R parallel with 2R, so we will be having equivalent voltage as R. So that is what so we will be getting. So here we will be having Thevenin equivalent voltage as 1.25. So in order to find out the voltage node V2, so the reference voltage will be equal to 1.25. So here we'll be having this resistance. So in this loop, if you are going to find out what is the voltage drop at V2, so V2 will be equal to, so 1.25 is reference voltage into 2R divided by 4R. So we'll be getting 0.625 as the volts. So again the Thevenin equivalent resistance used to have, so R 2R plus 2 parallel with 2R, so we'll be having Thevenin equivalent resistance. So in this configuration also we'll be having R. So this will be R again, this will be 2R again. So again at this node point, so if I want to find out what is the voltage across this node V3, so across this node V3, so 0.625 is the reference voltage, and the previous voltage drop will be 0.625. So that 0.625 will gets divided across this. So in order to find out the voltage drop across this. So V reference into 2R divided by 2R plus 2R, it will be equal to 4R. So 0.625 into 2R divided by 4R, that will be equal to 0.3125. So 0.3125, and correspondingly equivalent resistance also it will be equal to R plus R 2R, 2R parallel to R. So the equivalent resistance will be equal to R respectively. So R resistance is equal to R, and the voltage across here is a 0.3125. So 0.3125 into, so in order to find out the output voltage V0, whenever this corresponding B0 B0 bit is 1, so B0 bit is equal to 1, so we have found out as what, so whenever B0 bit is equal to 1, so that means whenever B0 bit is equal to 1, so you're going to get minus 0.625 voltage. So in order to get this voltage, so again, so we can see what is this, what is the voltage, total voltage drop across here up to here, it will be equal to minus 0.3125. So that is minus 0.3125 is the voltage across this when it comes over here. So minus 0.3125 is the voltage, and this is the resistance, feedback resistance, RF by R. So RF by R means 20 kilo ohm divided by 10 kilo ohm. So we will be having what? So 20 divided by 10 means we will be getting 2. So 0.3125 into 2, if I multiply, then I will get the output voltage as so V0. So V0 will be equal to V3 divided by R into RF. So V3 divided by R is what? So V3 is what? So V3 across V3 you will be getting as a 0.3125. So when you find, so this is a 0.3125 bರುತ್ತೆ. So V3 divided by R, it is nothing but 10k into 20k. So that is output of the amplifier, right? So output of the amplifier means you will be getting, so here at this point, because of this V0, because of this B0 alone, you are getting as this at this terminal you are going to get a 0.3125 voltage, because of all other bits are 0. So only because of this B0, so you are going to get 0.3125. Okay, so the equivalent resistance from this, if I am going to calculate, so it will be equal to R. So it will be equal to 0.3125 into resistance R will be there. So RF divided by R into V3. So if I do, so then I will get the output voltage V0 is equal to 0.625 respectively. So similarly, so when B1 bit position is equal to 5, so you will be getting when B1 bit position alone, if it is equal to 5, then what is this voltage across this? So it will be equal to, so it will be equal to when here it will be equal to R plus R to R again. So when B1 bit position is equal to 5, so if all the bit positions has been equal to 0, so B0 is equal to 0, B2 is equal to 0, B3 is equal to 0, only B1 bit is being connected to plus 5 volts mean. So 5 volts will be acting as a reference, and this will be the 2R resistance will be there, and equivalent from here to here if you find, so what is the equivalent resistance you will be getting? So 2R parallel to R, so it will be equal to R plus R, 2R. So 2R will be there. So 5 into 2R divided by 4R, so you will be getting 5 by 2, so 2.5 volts will be getting over here. So 2.5, and similarly if I'm going to have this, so again we can find out what is the bit position and the node position for only when bit position B1 is there, so you'll be getting all the reference voltage. So when coming to this terminal, so current will keep on reducing, and you will be getting the corresponding equivalent output voltage determined by this according to this equation. So when B naught bit position is there, so that will be equal to, so 2 power 4, so 2 power 3, 2 square and 2 power 1. So this is how we are going to get them where resistance, so minus RF will be the gate, so because it is an inverting amplifier, so we will be having minus RF into, so B3 bit position if it is connected to high, so you will be having equivalent resistance, so divided by 2R. So when B2 position is 1, so you will be getting divided by 4R. So when B1 position is there, so it will be having 8R. So when B0 is there, 16R you will be getting. So if I am going to substitute B0 bit as 1, so 1 divided by 16, so that will be equal to 0.3125. So 0.3125, and this RF and R, so you will be getting, so because this summation will be, so all this bit position if it is 0, so B0 bit is 1 means, so you will be getting, so 5 by 16, so 5 by 16 you will be getting, so 5 by 16 is nothing but 0.3125, so 0.3125 will be the voltage, and then so RF by R, so if you perform, so 20k divided by 10k, so it will be equal to 2 into 0.3125 will be getting it as a will be getting as a minus 0.625. Suppose if B1 bit position is 1, so B1 is equal to 5, so 5 by, so when B1 bit position is 1, so that will be equal to 5. So rest all bit position if it is 0, so 5 by 8 you will be getting. So 5 by 8 is nothing but what? So 1 by 1.3, so that is equal to 5 by 8. So 5 divided by 8 is nothing but 0.625. So 0.625 will be getting as this one. So RF is 20k divided by 10k, so we will be getting 2.5 as the output voltage. So minus 2.5. So when you connect B1 alone, so you will be getting the output voltage is equal to minus 2.5. So ಇಲ್ಲಿ 0.625 ಇತ್ತು. So when this bit position is there, so you will be getting 0.625. Suppose if both the bits are 1 1, so you will be getting, so for the third bit, so 0 0 1 1, so that is for that case, so you will be getting, this is nothing but what? So this will be equal to, so point so 5 by 16 means you will be getting 0.3125 plus 0.625, so that is 0.9375 as a output voltage. So that is what you will be getting. So the same thing here, 0.9375, so 5, so when this has been connected, so 0.9375 will be getting, multiply with 2, so you will be getting minus 1.875 you will be getting. So in this way you are going to perform all the calculation for all the bits from starting from 0000 to 1111. So when you are going to perform 1111, so you will be getting as what? So 1111, so you will be getting this as a 2.5 plus you will be getting 2.5 plus 1.25 plus 0.625 plus 0.3125. So that is a 4.6875 as the output voltage reading into RF by R. So RF is 20k divided by 10k, so it will be equal to 2. So multiply with 2. So that is going to get the full scale reference voltage as full scale reference voltage as 9.375. You will be getting as the full scale reference voltage. So this is what you are going to get. So when you substitute this, so the same thing. So minus 9.375 will be getting when all the positions are high. So multiply with minus RF by R. So that will be getting minus 9.375 full scale reference voltage you will be getting. So this is about the bit position. So in the exam they may ask you to perform by giving certain point as this one. So they will be asking, so what will be the corresponding output voltage? You should be in a position to do. Okay. So like this you have to do, and you have to find out what is the corresponding equivalent to Thevenin resistance, Thevenin voltage, and all you have to perform. And then finally you need to find out what is the node voltage across this every point. We need to find out what is this node voltage, and you have to find out what is the corresponding output voltage. So I have just done for when bit position is 0, so we have calculated, and finally have find out what is the node position you at V0, V1, V2, V3 respectively. So 2.5, 1.25, 0.625, and 0.3125. So like that you need to also calculate, and finally you have to sum up this based upon this equations we will be getting. So based upon this equation, when you substitute in this equation, so you will be getting this as the negative staircase waveform you will be getting. So for all the bit position is 0. So when 0001 position is minus 0.625, so 0.625, 1.25, so 1.875. So when you see from one corresponding bit position to this say next corresponding bit position, you can see the height as well as the width is going to be remain same. So for all the bits position, when it is 0, so you'll be getting 0 as the output voltage. When B3, B2, B1, B0, so when B0 bit is high, so you'll be getting the output voltage as minus 0.625, and 0010 if you find, so you can see again you're going to add 0.625, so that you'll be getting minus 1.25 respectively. So similarly, so for every input, so for every input in the increase in the input, so you'll be getting minus 0.625 as a step height. So minus 0.625 in the height, and you can see how many bit configuration are there. 15 configuration is there. So if you find, so what will be the corresponding the bits are high, so that is to 9.375 respectively. So this is the 9.375, you can see. So 0.625, so you are going to add 0.625 every increment, so you will be getting 0.625. So 0011, so you will be adding again 0.625 plus 0.625 you will be getting as for the third output. For the fourth output, getting incremented for every increase in the input, so you will be getting 0.625 as the step size. So step height you are going to get uniform step height. So this is how you are going to get the analog output waveform for even digital input. So that is, it has been written in decimal, whereas if you see, so as you increase the input in the binary, so corresponding analog output voltage you will be getting. So it is inverse. So inverse negative output voltage you will be getting. So negative staircase waveform you are going to get. So in this circuit, so this is the output voltage, how you are going to find. And similarly, so there are since it is going to be has become popular because of only two resistors are used in this, and also the speed of the conversion is also fast. So you are going for digital to analog converter, so R to 2R DAC only. So at present, so there are various 8-bit, 10-bit, 12-bit, 14 and 16-bit digital to analog converters. So you can since you are going to deal with only two resistors, so any number of inputs bit conversion if it is required, so you can perform. There is no specific criteria that you have to use the specific resistor, so only two resistors. So as you increase the number of inputs, so you can easily adapt to for the conversion rate is also possible. So it is going to provide accurate as well. So we can have any number of bit conversions are required, so you can use this one. So 16-bit DAC with a current output, so you can have any type of output. So current, if you want a current output or voltage output, or both current and voltage output, so you can use for this number of input digital to analog converter. And now if you see, so for an 8-bit digital to converter, so in an IC when you are going to use, so digital to analog converter, so they have specific parameters that need to be supported, so that need to be satisfied. So these are some of the specifications that you need to consider when you're going to choose a specific converter. So what is the resolution of the DAC? So because digital to analog converter for a given application, it is required to see these are the important because the resolution, linearity, gain error, as well as the settling time. So these are some of the important parameters that they need to be checked for any digital to analog or analog to digital converter is considered. So the resolution is nothing but, so it is nothing but it is a so resolution is determined by number of input bits of the digital to analog converter. So how many number of bits so corresponds to one part in the number of bits. Suppose if it is a 8-bit converter, so 8-bit digital to analog converter means so you'll be having 2 power 8 configuration. So in this previous case, 4-bit positions was there, 4-bit DAC was there. So 2 power 4, that will be the number of input combination. So 2 power 4 means 16 input configuration was there. In that, what is the minimum output level? That is for a resolution. If I want to find out what is the resolution means, it is nothing but one part of the total number of input configuration. So one part of 256. And the previous case, if I find, so one part of the 16 configuration, 1 by 16. So that will be having. So here 1 by 16 plays a major role. That is nothing but the resolution of that corresponding circuit. So resolution value is the LSB. So where the LSB bit position is there, so for that corresponding value, so one part of that, so that is nothing but the resolution. For that corresponding, what is the output voltage we have got? So when the bit position is LSB bit is 1, so we'll be getting minus 0.625. So that 0.625 refers to the resolution of that corresponding output voltage. So non-linearity as well as linearity error. So that is non-linearity as well as linearity error means, so you can have seen this negative staircase waveform. So this is nothing but predicted. So this is a predicted output based upon based upon this expression. If I find, so I should get this as the output. That is a predicted output we should have. But actual output, because of if anything varies in between the resistance and all, so there will be some deviation from the predicted output as well as the actual output. So that is nothing but a linearity error. So how much the difference between the actual output of the DAC with respect to ideal straight line output. So ideal straight line means predicted. So based upon the equation, so what should be the exact output you should get. But the actual output what you have got, so that shows the difference between those two. So that gives the linearity error. So linearity means ideally you should have the straight line. So that means you should have equal step height as well as step size. But if it is deviated, then that is called as a linearity error. And the gain error and the offset error. So gain error is nothing but a deviation from the feedback resistor. So gain error means so we know that what type of op amp you are going to use and what is the gain corresponding to that corresponding op amp. So if it is converted into connected in the inverting configuration, that means you will be getting will be getting as a gain as minus RF by R1 R. So that is a gain. So for the corresponding, so if it is connected to the non-inverting terminal means 1 plus RF by R. So that gives the gain. So if it is having any gain error, so that is nothing but gain error. And offset error is also considered, because offset error means you already have just explained in the previous module itself. So what do you mean by offset? So offset is nothing but the unwanted. So unwanted. So when all the bit positions has been connected to 0, so if you are going to get any output voltage, then that is nothing but the offset error. So the same thing here also they have mentioned. So on the other hand, offset error implies that output of the DAC is not 0. That means, so ideally what is the output when all the bit positions are 0? So I should get 0 as the output voltage. But if all the bits position are 0, so if I'm not going to get the DAC output some output voltage if I'm getting, then that is nothing but that error is called as a offset error. So settling time. So what is the time required for the output to settle within the plus or minus half LSB of the final value for a given digital input? That is nothing but a full scale reference output voltage. So that is nothing but a settling time. So how much time? So what is the how much time it is required in order to get settled for the full scale output voltage. So for plus or minus half LSB, so LSB is nothing but the least significant bit, so plus or minus half LSB, so how much time it is going to get. So as soon as I connect to for a given to 2-hour ladder with this corresponding through the any counter anything, so you should get this output frequently. So how much time it is going to get settled for the output to get settled. So that is nothing but the settling time. So this is about the R to 2-hour ladder technique. So this is for a 4-bit binary digital to converter, and this corresponding equivalent how we are going to find that has been denoted over here. So in the exam, they are not going to ask only the architecture as well as circuit diagram. So they may ask for a given input configuration, what is the corresponding output voltage, how we are going to get. So they may ask you in the final exam. So this is the corresponding output voltage, analog staircase waveform, inverted staircase waveform. So that corresponding input configuration and corresponding output voltage, they have noted down in the, they have shown in the tabular column. So the same thing, they may ask you to find out the corresponding output voltage, and you write down the corresponding expression for this to find out the output voltage they may ask. So that is one important task, so that you should know. So 0002, all the bits position if it is equal to 111. So what is the corresponding output? So complete. So calculate the output voltage for this configuration. So that is 1011 configuration if they ask me. So you should get this as the output voltage, and you need to show how you got this output voltage. So by using connecting all these equivalent resistance, equivalent Thevenin, equivalent voltage and all, you need to calculate and you need to show. Is it clear? So with this I'll just conclude today's class. Thank you. Any doubt is there? So with respect to today's topic, so
No, sir.
okay then. So I will just finish it now.